Hello. This is going to be really fairly simple. Remember the last video we talked about the fact that the largest side in a triangle would be opposite the largest angle, and the smallest side would be opposite the smallest angle, and vice versa. What we have here is basically the same thing, except that we're talking about two different triangles. And in English, all we're really saying is, other things being equal, a side opposite a smaller angle will be shorter than the side opposite the larger angle in two different triangles. Before we were referring to only one triangle. For instance, if we had this triangle here, if this is the largest angle in this triangle, then this is the largest side. Okay, that's within one triangle. Now we have two triangles. What we're saying here is that this side is congruent to this side. This side is congruent to this side. So the segments forming the angle are both congruent. In a case like that, the size of the angle is what determines the length of the opposite side. It's important that these two be congruent. So I think you can easily see that that wouldn't work if they weren't congruent. Now you have to remember that, say in a case like this where these two angles are congruent, if this angle, suppose they weren't congruent, suppose this angle was a little bit bigger than this one, we still couldn't say much about which side was bigger, because these sides aren't the same length. If you extend farther out here, the side opposite this angle just gets bigger and bigger. The farther out you go, the larger this side gets here. Right now it's right there. As you go out, it gets farther. It gets distance from here to here gets longer, and this side increases here. So even if this was a little bit larger, you could draw the angle out here, and now this angle is larger than this angle, but this side is still shorter than this side. That's because these two sides are not congruent. See, the whole crux of this theorem is that, like I said in the first place, other things being equal, other things in this case being the two sides of the angle. If these two sides are congruent to these two sides, now we could make a statement about the included angle and the opposite side. Namely, the larger the included angle, the larger the opposite side, and the converse, of course, is that the largest side would be opposite the largest angle. In other words, ACB is larger than DFE. Why? Because the 12 is bigger than 9, and because these two legs are congruent. That is an extremely important part of this. These two legs are not congruent. None of this means anything. However, if these two legs are congruent, I don't think the result is any kind of a surprise to you. This is very much, in fact, almost identical to what we did in the last video, and we pointed out, if you've ever held a door open for somebody carrying something large, you figured this out. A larger angle means a bigger opening here. That's about all these theorems say. The previous video made that statement for the angles within one triangle. Now we're making the statement for the angles in comparing two triangles and saying that the side of this triangle is larger than the side of this triangle because the included angle here, this included angle is larger than this one. And the second thing we'll look at is proof by contradiction, also called indirect proof. I don't like indirect proof. I like proof by contradiction because I think it's a better description. It's more accurate. That's what it really is. Remember, I pointed out if you wanted to prove that 2 plus 2 equals 4, it's pretty hard to do in terms of a direct proof. However, if you start with the converse, and that's what proof by contradiction is, you start with the idea, or say the hypothesis, 2 plus 2 does not equal 4. And I think yesterday I started with 2 plus 2 is greater than 4 and wound up with a contradiction. Well, that just proved that you can't have 2 plus 2 greater than 4. 2 plus 2 not equal to 4, you have to consider both cases. I considered the first case in the previous video. Now, if we really want to prove, we have to consider the second case. There are only two ways to be not equal, either less than or greater than. We're talking about numbers now. Congruence is different. There's all kinds of ways to not be congruent. But we're talking about numbers and equality now, and that's a little different. So we subtract 2 from each side and get that 2 is less than 2. And now we can point out from our reflexive, that's not the reason for that, but this can't happen. 2 less than 2, not possible. And that's from the reflexive property of equality. We started by assuming that what we wanted to prove wasn't true. And then we wound up with the contradiction, which means it must be true. This is maybe a little bit related to the idea of contrapositive and the truth of a contrapositive. Remember, if we have an expression P implies Q, the contrapositive was not Q implies not P. If this is true, then this is true. And a simple example would probably make this obvious and maybe easy to remember. If it rains, you get wet. Now, you can't say if you're wet, it rained. There's other ways to get wet, but one of them is rain, which means you can draw this implication. Rain means you get wet. Now, let's take the converse. You're not wet, therefore it didn't rain. Well, that actually makes sense. It says that what must happen, that is the unavoidable conclusion of P is Q. If Q doesn't exist, then P must not have happened. And in our concrete example, if you're not wet, it must not have rained. That's sensible. You're not really making a sweeping statement. You're not saying, if he's wet, it rained. No. All we know is, if it rains, you get wet. There are other ways to get wet. Gee whiz. But, if you're not wet, you can definitely say that it didn't rain on you. Now you can see the sense of why, if this is true, this has to be true. Because Q always follows from P. If you don't have Q, then P must not have happened. Well, now that we've got a couple more pieces of new information, let's see what kind of trouble we can get into. Which is a possible measure for JKM? JKM. So, that's this angle right here. Well, what do we know? We know that this is an isosceles triangle. So, if it helps, we know that these two angles are congruent. That probably doesn't matter. This is congruent to this, and this, of course, is congruent to itself. So we can consider these to be two separate triangles. The included angle has congruent sides, which means that the larger angle has to have the larger side, and the smaller angle has the smaller side. opposite it. And remember, that's true because this side is congruent to this side, and this side is, of course, congruent to itself. Which means this angle has to be less than 25 degrees. Well, luckily, only one choice here is less than 25 degrees. 20 degrees is the only possibility. In reality, all we know for sure is that it is less than 25 degrees. But in a case of a multiple choice, only one of these is. So this one is a possible measure. We don't know that it is, it's just possible. And here we have a case of a reporter who tried to study geometry. And naturally, in keeping with his profession, he didn't get anything right. Let's see where he made his mistake. What do we have here? Well, we've got a congruent side and a congruent side. Okay. And this is congruent to itself. So, we could compare this angle and this angle, since that would be the included angle. But he's using the Hinge theorem to determine that PQ, that's this one, jeepers, is less than SR, that's this one. So he's using the angle closest to the side, not the angle opposite the side, which is not what the Hinge theorem says. The Hinge theorem says that the side opposite the angle is larger or smaller depending on the other angle. Well, to use the Hinge theorem, you've got this congruent, and this of course is congruent to itself, so you'd have to know this angle here, and then you can make a statement, well, you don't have to know this angle here, and then this angle here, and then you can make a statement about PQ and SR. For instance, if this were 44 degrees here, and this were 46, then PQ would be less than SR. But you can't do it this way. It has to be the included angle. And you probably noticed that right off. And here he is using the Hinge theorem again. Well, he's got the right idea. This side is congruent to this side, and this side is congruent to itself. So this has to be the larger side, because this is the larger angle. And he just got it backwards. Well, it's a nice thing about reporters. They're consistent. Now here they'd like us to use the Hinge theorem, or its converse, to solve an inequality. Well, let's see here. What can we do? Let's see, this is 12 and this is 12. Okay, that means they're congruent. This is congruent to itself. So we have an included angle and an opposite side, an included angle and another opposite side, and it looks like this angle is opposite a smaller side. Everything else is congruent, so this angle must be smaller. So we can write 2x plus 5 is less than 66. Or 2x is less than 61. Now subtract 5 from each side. 2x is less than 61, or x is less than 30.5. Is there anything else we can do to restrict the value of x? For instance, say, find a range. We don't have any information that would allow us to do that. I think later on in trigonometry, if you get good at it, you could find a range in here. In fact, you might actually, based on this, you might actually figure out exactly what this angle was. But we don't have enough information to do that. I think all we can say is that x has to be less than 30.5, because x has to be less than 66 degrees. That's about all we can say right now. Here's one that's, I think it's kind of weird because I'm not sure we have all the tools to actually prove what we're going to do. So in the end, it seems to me it almost relies on us visually identifying an angle. I find that pretty unsatisfying. And there should be a way to quantitatively prove that this angle H here has to be obtuse. And what they're asking us to do is to show that this side here is longer than this side or this side. And they have given us that FH and GH are angle. They are angle bisectors. Now, we know some things it's tempting to throw in, but in the end I don't think it'll help. For instance, FH plus HG is larger than FG. But that doesn't say that FG has to be larger than either one of them, taken individually. There's only one thing I see that would make this definitely, provably longer than either of these. And that is this angle here. Looks way bigger than either of these two. How do we show that it's bigger? Well, these two angles are half of the original angle in this triangle, right? This is an angle bisector, so these two angles are congruent. In fact, we cut them in half. Now, the largest obtuse angle you could get would be 180, at least in terms of a triangle. And if you have a 180 degree obtuse angle in a triangle, you don't really have a triangle, you have a straight line. So any angle in a triangle has to be less than 180. Well, if you cut something less than 180 in half, you get something less than 90. And anything less than 90 is an acute angle. So if you follow the reasoning there, this angle, say F for instance, has to be less than 180. So half of it is less than 90, which means it's acute. Same thing over here. So these are two acute angles. That doesn't prove that this has to be obtuse. It doesn't. You can have three acute angles. However, it might be legitimate to eyeball this and say, well, that's at least 90 and probably bigger. I mean, 90 would be off like this. Follow my pencil straight up. That looks bigger than 90 to me. If you're allowed to use visual references, then H is definitely larger. In other words, I should do it properly and say that FHG is definitely a larger angle than HFG, simply because this is an angle that's been cut in half. And any angle in a triangle, once you cut it in half, the two halves have to be acute. There's no way around it. And this certainly looks obtuse. I haven't noticed a theorem in here which proves that angle bisectors would intersect at an obtuse angle. If we had a theorem that told us that, then we could definitely prove that this is the longer side, because we could definitely say that this is an obtuse angle. It certainly seems like it. I mean, this looks obtuse. There may be a way to prove that angle bisectors will intersect at obtuse angles, but I don't think we have that. I drew an extra bisector in here just to figure out if it was even possible to prove that angle bisectors would intersect at an obtuse angle, and of course it isn't, because it's not true. Here's an angle bisector here, here's one here, and I would say that's definitely an acute angle. I admit I'm just eyeballing it, but that's what's unsatisfying in my opinion about this problem. We should be able to point to some theorem or postulate which says that this angle is definitely obtuse, which means it has to be larger than these two. As it is, we're just eyeballing it. And it seems to me if you're just going to eyeball it, why not just eyeball this and say, well, this looks bigger than those two, so it's bigger. I'm not sure why it's more quantitative or accurate to eyeball the angle than to eyeball the side. Well, we don't have the theorem yet. At least I sure couldn't find it. But there should be a way to prove that if we use angle bisectors to connect the vertices, in other words, we're just skipping the extension of the bisector here and just drawing the bisector from the vertex to the point where all three of them intersect, what we're calling the point of concurrency. If we do that, it appears that these angles will always be obtuse. For instance, I can distort this quite a bit, and yet I can't find any way to distort it that would prevent all three angles from being obtuse. For instance, if I stretch it way out like that, I get really close with these two angles. As I bring this down and stretch this out more and more, this side will come down and down and down until this gets down to this part right here, becomes a right angle. Problem is, when it becomes a right angle, these two sides coincide with this side, and it's not a triangle anymore. It's not. So we would have two 90 degrees and then this here. But if this were 90 degrees, I don't see how this could ever be an angle bisector. In other words, these two are 90. Then this would drop down and be like 0, I guess. I don't know. How far out can we get it? We can just keep, stretching it out. But as we stretch these two vertices farther and farther out, and this line drops down, the farthest it could drop is right down onto this line, which could never actually happen. That's a limiting situation. And that would make these two 90 degrees. So visually, I think you can see that there's no way that these can avoid being obtuse angles. For instance, if I were to, I could stretch it out in the other direction, but you just have the same problem. You'd never get acute angles in there. Is there a reason for that? Is there a way to prove that? Oh, definitely. It's very easy to show. We just don't have the tools that will show it yet. But if we were going to do that, here's what we'd do. As I say, it's really easy because all you have to do is make use of the fact that all the way around, that has to be 360 degrees. We also know that 180 is out. So how could you have three angles that add up to 360? None of them could be 180. And we were able to show, at least visually, at least it looked like we'd never get down to 90 degrees for any of these angles. None of them would ever get lower than 90. For instance, if they were all equal, that would be 120 degrees apiece, 120 in each one, if these were all equal. Now, is it possible to get 360 degree and still have an obtuse angle? Well, let's see if we can draw one. I drew a point here and then used acute angles and drew it out just like here, but suppose this line right here actually extends out that way. That puts this vertex over here. We can only have three vertices in a triangle. So if this comes way down here, so we have an acute angle, that puts it down here, and it looks more like we've got two sides of a pyramid. We don't have a triangle when we connect it up this way. Again, this is not a rigorous proof. This is just a visual way to see that these all have to be greater than 90 degrees. If you drop this down, right down to here, then the angle this makes with this one and the angle of this line makes with this vertical line would both be 90 degrees. But that wouldn't make any sense, because that would push this point way down here, and you would just have a straight line, and that's no good. Well, that took way too long, but hopefully, if you've sat through this whole boring 10 minutes, you will never forget that when you connect up the angle bisectors, you will always have obtuse angles in between the sides here. In other words, you create more triangles. Did I do that down here? Yeah. When you connect them up, you're always going to have obtuse angles here. There's no way to get around it. And if you remember that, then I guess it was maybe 10 minutes well spent. Who knows? Well, there's another simple example of proof by contradiction, or indirect proof, whichever term you like. Now, they gave us the statements we're going to use to prove that an equilateral triangle is also equiangular. Well, let's see where we would start. If we're going to use proof by contradiction, normally the first thing you do is assume the contrary. That is, assume that it is not equiangular. Now, let's see if that's up here somewhere, this contradiction. Ah, here we go. They always say temporarily. I don't know why. I just say assume it and maintain that assumption up until it is proven wrong, at which point you've hit a contradiction and you've got your QED. So when I say assume, I guess I don't really mean stick to it and refuse to drop that assumption no matter what evidence to the contrary pops up. No, just assume it. And then your assumption turns out to be wrong, you drop it. So our first line would be E. Now, what would our second line be? Well, if we assume that they're not equiangular, then some angle must be larger than some other angle. That's what it means to be not equal. One thing's larger than the other. So they just arbitrarily pick a couple of angles, and there must be some angle P which is larger than some angle Q here in the triangle. I think that would be our second statement. Now, if one angle is bigger than the other angle, let's say P is larger than Q, just as they did, then this segment here must be larger than this segment. That follows from the fact that the angles aren't equal. If the angles aren't equal, then the larger angle is opposite the larger side. The smaller angle is opposite the smaller side. So, the second we write this, we can then write this. That's D. So now we have, well, I would say, this contradicts the statement that it's equilateral. So I would say fourth thing we write is B. Because QR larger than RP contradicts the statement that PQR is equilateral, because the definition of equilateral is that every one of these sides are congruent. So, I guess our next statement is this contradicts the given statement, so the contradiction shows that the temporary assumption, if you want to call it that, the assumption, which we're going to toss out because we're going to prove that it's a bad assumption. No, the assumption is false. Is not equiangular, must be false. So that's C. I think that's all of them. A, B, C, D, yeah. And I think we have them all in order. So this should have been number 1. This over here would have been the second one. The third one was down here. The fourth one, and the fifth one is right here. Not too bad. And you probably see lots of things like that on the standardized test. Mostly because it's easier to give you choices. It's easier to correct when you're given choices. If you do it free form, it takes forever to correct something like that. So hope and pray for lots of stuff like this. It's way easier to match up than it is to just pull it out of the air. Here's a quick, easy one. Well, it's quick and easy if I don't do too much writing. I'm going to be lazy about this and show you how you would do this. It's really pretty simple. Just like all indirect proofs or proof by contradiction, which I admit, as I've mentioned before, I like that name much better. Because it's just like what it is. You just make an assumption. What you do is you assume the opposite of what you're trying to prove, and then you hit a contradiction, which shows that your assumption must have been false. So what it was you were trying to prove must actually be true. And what we want to show is that the shortest distance from a point to a line is the perpendicular segment. That's this here. But suppose it isn't. This isn't perpendicular. I'm just telling you, it's not perpendicular. It's not because it doesn't look perpendicular. I drew it to not be perpendicular. First off, we already know that the shortest distance is going to be some kind of a line. In other words, we know from previous theorems that our shortest distance is not going to be that. That's never going to work. And it's not going to be that. It's also not going to be that. It's not going to be any curve. Okay? So let's forget about all the curves from the line to the point. Let's consider a line from the point back to the line here. Now let's say that this is the shortest, right here. This is the shortest distance. Okay, fine. Now, let's drop a line down here from the point, actually, a line segment down here, which, I'll put it in here, which is at right angles to this right here. It's at right angles to this line here. Well, what do we have? We've just used this and this as two sides of a right triangle. We draw this in and now we've got a right triangle. Well, remember the sum of the angles in a triangle has to be 180. If this is a right triangle, that means this is 90 degrees. Well, these two have to add up to 90 degrees. Neither one of them can be 90 degrees. They both have to be less than 90 degrees. They don't have to be a lot less, but they have to be a less. In other words, they have to be acute. There's no way around it. In fact, we have a theorem that says that if you have a right triangle, you have a right angle, and the other two angles have to be acute angles. Well, a right angle is larger than an acute angle, isn't it? Well, we know from our Hinge theorem that the opposite side, the side opposite the largest angle, is the longest side. Well, wait a minute. We already decided this is the shortest distance from here to here. If this is the longest side, that means this is shorter, which goes from the line to the point also. Well, if this is the longest side, and we assumed it was the shortest distance, that doesn't make any sense. That's a contradiction. And that's the way you would lay this out. It's real simple. You just draw any line that's not a right, that's not perpendicular. Any line that doesn't form a right angle here. Pretend, that's even better than assume. Let's pretend this is the shortest distance. All we have to do is draw a line right down here, perpendicular to this line, and then point out that this is 90 degrees here. These two are less than 90. This must be the longest side. But that contradicts our original assumption, which was this was the shortest distance. So, boom, you're done. Pretty easy. Well, that's about it for now.